So my essential problem is the following. Change the variables chi tilde to the first order and then calculate this Lagrangian change at the first order and make it equal to 0. So all of you agree now. So my essential way of doing it would be change all chi tilde from the original chi tilde plus delta chi tilde. So this is my new value, let's say chi tilde ends, and then I calculate delta L tilde. Okay, so delta L tilde is nothing but first order change. So this is first order change in the Lagrange. And put it equal to 0. So you all agree that this is the first order change, right? So this is basically doing the derivative equal to 0. So I don't have to consider second order change and then divide by delta chi tilde and then limit. So all that I don't need to take. It's a very simple thing. So just make each of the chi tilde change to first order and then calculate the first order change in delta. The change from the origin and make it equal to 0. Is it clear to everybody? So that will be basically doing the variation. And of course, now I'll have to go through the algebra what the first order change means. So that will go slowly. Note again, there are two kinds of chi tilde, one on the left, one on the right, everywhere. So I have basically chi tildes as well as chi star tildes, correct? Now the question is, do I need to change both of them? The answer is no. Because they are complex conjugates, I can only change one of them. Let's say complex conjugate of the chi, so left one, and then find out what is delta L tilde and make it equal to 0. Because the other one will be simply complex conjugate of them. So I don't need to do it twice. So I can only change the chi tilde left side. So basically I am changing chi tilde star. So that's easy to chop off from the left side. There is no particular reason to choose left side. I can make right side. So eventually I am going to make each of the left chi star from chi tilde star to delta chi tilde star. First order change and see what happens to the delta. So I think you can now do this. Of course, when I am changing chi star, remember the chi is also changing. Obviously, because I can't change only the complex conjugate and not this, because they are conjugate to each other. So both of them are changing to the first order. So let us now write down what happens as a result of the change. Alright. So let me first do the first term. First term is very easy, fairly easy. So let's do the first term. Remember, I am changing each of the chi tilde. So what happens for the delta L tilde for the first term? So this is only the first term in that expression. So what would be the result? It will be sum over I. Remember, I am writing delta. So I am going to subtract this term for each term. So I will now take only first order. So first order will be delta chi tilde on the left, H chi. Is there any more term? Yes, plus chi tilde H delta chi. Tilde. Sorry, tilde. That's all. Do you agree? Because of course I will have another term where both of them are delta chi tilde, but that is second order. So I will not consider. So delta L tilde, because of this change, we will have one side delta chi tilde, another side just chi tilde, and chi tilde delta chi. Because when I am changing either one of them, the other one also will change. So the first order change of chi delta L tilde for this term can be written very simply. Yeah, it will have an effect, but we are taking orders of only delta. First order in delta. Whatever is the delta we define. So Hamiltonian, please remember, the small h does not have chi. So when I am changing chi, the Hamiltonian does not change. The physical Hamiltonian does not have chi. So the small h is a one particle operator, that will be constant. So that's why there is no change here. And of course, this h will act on that actual integration. It's a one particle integral, so you don't have to bother. This is a function, this is a function, integral. Of course, this function is not equal to this function. This is a change, very small function, and there is an operator. This one, so it's a one particle. So, for example, this one is nothing but chi I star, whatever is the dummy variable, r, h of r, delta chi I. So that is this integral. So these integrals can be trivially done. Actually, I have not defined what is delta chi I, remember, and it's not important to define. You will see the later, but it's just a first order change. Assume whatever is the first order change. So note also, when I did this problem, remember this first order change is for any delta x. So it is an arbitrary delta x. So this change that we are defining here is for an arbitrary delta x. I am not defining even delta x. Any arbitrary delta x that you can do. So that will anyway cancel out when you do dy dx. Okay. So I did this. Now let me go back to the second term. The second term is fairly complex, as you can see. First of all, the second term has two terms. It is not one term, it is the Coulomb and the exchange term. So let me write down delta L tilde and let me call this term 2a. So 2a is essentially the Coulomb term for the second term. So if I write this, you will get half of sum over ij. So you have the Coulomb term, and I have to take the first order of the Coulomb term. So remember, there is a 1 by r12 here. So I am going to now write it explicitly. So I have a delta chi I tilde. This should now remain chi j tilde. 1 by r12 chi I tilde chi j tilde. Agreed? This is the first term. Then I can change chi j tilde. Because remember, this is for all chi I, a dummy variable. So there will be another term which will be chi I tilde, delta chi j tilde, 1 by r12 chi I tilde chi j tilde. Further, there will be a third term which is chi I tilde, chi j tilde, 1 by r12 delta chi I tilde, chi j tilde. And there is a fourth term which is chi I tilde, chi j tilde, 1 by r12 chi I tilde, delta. I think all of you can write it very easily. So for original integral, which is chi I tilde, chi j tilde, 1 by r12 chi I tilde, chi j tilde, you are just changing each of these four one at a time, because everything is first order. So I can't have any two changes plugged in. So I'll have only one change at a time. Is it clear? That's the Coulomb part. Then comes the exchange part, which is more difficult to write. Simply because I have to switch this. Okay? Eventually, of course, I have to switch this. So chi j tilde 1 by r12 chi j tilde chi I tilde. So I can write this delta L tilde to b. So I have to be just careful. So this should be equal to half of delta chi I tilde chi j tilde. So same terms I am rewriting it again, 1 by r12, except that the right hand side will now all change. Chi j tilde chi I tilde plus delta chi I tilde chi j tilde chi I tilde delta chi j tilde 1 by r12 chi j tilde chi I tilde, and so on. You can write this, all these terms. I'm just writing it, but it's very easy. And to a point that it is quite boring actually. Okay? And hence the fourth term, I should just write with a minus sign. Whole thing is minus. Okay? So for everything I have just exchanged the right side, and since this comes with a negative sign, I have to make minus for everything. So this up to here, it changes. Actually, let me put this outside. Should be minus half. Okay, the half also multiplies it. So minus half of all this. Do you agree? So you have the delta L1, delta L2A, delta L2B, and finally, of course, this term, last term, delta L3. So let me write this down as well. So delta L tilde 3 equal to minus, I put a minus, sum over ij, and then I had a lambda ij, which is just a number times delta chi I tilde chi j tilde plus chi I tilde delta chi. Right? Of course, the first order change for this quantity, lambda ij into delta ij is 0. So I am not writing, I am writing the change because that's a constant. Kronecker delta is a constant. This is also a constant. So I am not writing this minus delta ij because we are writing only the change. Okay? So that will anyway get cancelled, whatever is constant. Is it okay? So now I have got everything in place. So I can write down the entire delta L, except that there are too many terms. That's the only problem, specifically because of 2A and 2B. And so we'll try to look at this term a little bit more carefully and try to analyze this. Okay? The first set of terms and the third set of terms are fairly straightforward. You have this, 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 and this. Out of which, if you notice, this term and this term are complex conjugate of each other. I hope you can see that. So if I take conjugate of this term, what will happen? How do I take conjugate? This one will become the left vector. H is a Hermitian operator, so it will remain same, and this left vector will now go to the right. I hope all of you remember how to take matrix element conjugate. So if I have an operator A, and if I have a F, phi and psi, what is the conjugate? Conjugate is nothing but psi, a dagger, phi in general, and for Hermitian operator, it is psi, a, phi. Right? Okay, so just remember this, how to take matrix element conjugate. Just take the conjugate from right to left and put it down. For Hermitian operator, of course, you have a special simplification. So you can notice that this part and this part are complex conjugates of each other. If you do the same exercise, you can clearly, here it's more difficult to see because here there is a sum over I in both. I hope it is clear that the sum over I for both. When I do it here, it is a little bit more difficult because this is delta chi I chi j, this is chi I delta chi j. So by itself, this is not a conjugate of this. Yes. However, there is a summation over all ij, dummy index. If I take the entire summation, then the sum of these and sum of these are conjugate to each other because I can interchange the dummy index. I hope all of you understand. If not, I will pause a minute to get that point very clear. So essentially what we are doing is the following, that I have a set which is sum over I j, lambda I j, delta chi I tilde, chi j tilde, and then I have another term which is sum over I j, lambda I j, chi I tilde, delta chi. So I have to show that this is conjugate of this. Before I do that, let me also mention a very important part, that the Lagrangian by which I am starting, the original Lagrangian, just like the energy, is of course Hermitian. It has to be Hermitian. So that is one of the important constraints that I will have, because the energy has to be Hermitian. Eventually I am going to calculate energy. So my Lagrangian has to be Hermitian. So one of these constraints is, because of this, you have to see that the lambda is a Hermitian matrix. Of course, if it is a real, then it is very easy. It's a symmetric matrix. Otherwise, lambda has to be a Hermitian matrix. I hope that is very clear, because you look at the Lagrangian. What was the Lagrangian? This part. This part was ij, lambda ij, chi I tilde, chi j tilde, minus delta I. So that was my if this has to be Hermitian, so you can see that I can always interchange this part for a dummy variable, no problem. But when I interchange ij, this lambda will become lambda j, dagger, right? So unless this is Hermitian, the whole thing will not be Hermitian. So right away we have a situation that to start with, my lambda is a Hermitian matrix. If lambda is a Hermitian matrix, it is easy to show that this is conjugate of this. Now normally lambda is just a real matrix, so it's actually symmetric. It's not even, Hermitian is really pushing it too far, because these are all real numbers in actual cases. So they are actually real symmetric matrices. So you can see what happens now. If I take a conjugate of ij, lambda ij, delta chi I tilde chi j tilde star. So if I take a star of this, what will happen? I am taking a star of the entire summation, not each star. So what will happen? This will give me sum over ij, lambda ij star, delta chi j star, delta chi, correct? Just as it occurs, chi j delta chi j star is not necessary, chi j delta. Then I interchange the dummy variable, call I to j, j to I. So this remains sum over ij, and if I interchange dummy variable, this becomes lambda ji, which is actually same as lambda ij, if the real number, otherwise it's a Hermitian matrix. So I get the same thing, lambda ij, and this then becomes chi I delta chi. Okay, which is exactly the same as this. So the conjugate of this term after summing is equal to this term after summing. Is it clear? Because of the fact that the lambda is a Hermitian matrix or a real matrix. So if somebody asks you to prove that these are conjugate, you should be able to prove very, very clearly. Okay? So first part of the proof is that since lambda is Hermitian, L is Hermitian, this lambda is a Hermitian matrix. So this is where it starts. And then it is very easy to show that these two terms are conjugate of each other. So I have a situation in the delta LA, delta L1 and delta L3 is that I have two sets of terms which are conjugate of each other. So that's important to remember, that I don't have to write. I can simply say that this plus complex conjugate. Similarly, this plus complex conjugate, CC. See, CC is essentially short form of complex conjugate. I don't have to write it. Then we come down to the analysis of 2A and 2B, which actually has a large set of terms. So we have to analyze this. Now, if you look at this set of terms, we have to see whether there is a conjugate which exists here. If you take the conjugate of this term, what will you get? You will get chi j chi I, correct? On the left, 1 by R12 chi j delta chi I, which is actually same as one of the terms. Right? Either of these doesn't matter, because again there is a dummy variable ij. The same exercise I can do, and I can show that these two terms and these two terms are conjugate of each other. I hope all of you will be able to show this exactly in the same manner, because of dummy variable interchange I and j, they would be conjugate to each other. And in the same manner, the 2b also has two sets of terms, that this set is a conjugate of these two sets. So what is interesting is that the entire thing can be written as a set of half of the terms plus complex conjugate. Is it clear? Okay, so let me now try to write down the delta L in this manner. So I will only write the half set of terms. So I won't write the entire set of terms. And for the sake of consistency, that half set will always contain the change on the left side. Okay? So the first set is delta chi I tilde H chi I, sum over I. Okay? I'm going to put the complex conjugate later for all terms. So I'm not writing this. Then I go back to 2A and I write this as a half of ij delta chi I tilde chi j tilde 1 by R12 chi I tilde chi j tilde. And then the second term I am only going to write these two terms now. However I want to write, I will write. The second term is chi I tilde delta chi j tilde 1 by R12 chi I tilde chi j tilde. I don't choose to write it like this. What I will do, I will make a further dummy variable interchange here. I will make this I will make this j deliberately. So then this will then become plus delta chi I tilde. Sorry, these tildes I am forgetting sometimes. Chi j tilde 1 by R12 chi I tilde chi j. Okay. So these two sets of terms, and then I will have the exchange similarly. So you can write down the exchange similarly as delta chi I tilde. So just do the exchange here. Chi j tilde 1 by R12 chi j tilde chi I tilde, and then minus half. Yeah, it's better to write each of them separately, because again I want to make sure that this interchange is possible only over the entire sum, not for each ij. So that's the reason I'm writing it separately for the time being. Delta chi I tilde chi j tilde 1 by R12 chi j tilde minus sum over ij lambda ij delta chi I tilde chi j tilde. That's it. And then I just say that whatever it is plus complex conjugate. All the terms you take conjugate. Is it okay? With a sum over I can actually, I'm actually allowed to write this. That is important when I do a sum over I. Now, there is, of course, I'm going to make it 0, equal to 0. What was the reason I did this? You know, why did I make such a tweaking that I didn't want delta here? The reason is, if I have this, I can apply a very simple rule, which I will tell you now. So, no, if I do this sum, it will be identical. It's only for, not for each ij. So please do that sum first. The reason I want to write is the following: that let's say I have an equation which is delta chi I star, and blah blah, everything is there. Something is there, integral is equal to 0. You know, something is here. Don't have to bother. Some function of whatever. If I integrate over the all variable, it is equal to 0 for all delta chi star, sum over I. Then the first thing that I will do is a sufficiency condition. To make it equal to 0, I will say that for each I, it is 0. For each I, if it is 0, then I don't need to write the sum. I don't need to write the sum. So I will say this is 0 for each, all arbitrary delta chi I star. Then what does it mean? This means that this will become equal to 0. I hope all of you know the integral, that if I have x star y 0 for all x, then y is 0. And that is a strict condition for the for the 0. So if I have a very simple condition that a b 0 for all a, then b is equal to 0. This is a very strict equality. So that is what I am going to apply actually. Eventually, delta chi I star 1 and something is there which I don't care. Something is there, so that something must be 0 on the right of the delta chi I star. So that is the reason I am doing it. Now you may have problem, because you may say this is only A1, B1, 1 electron integral, here you have 2 electron, but that's really not the point. I will show you that's not the point by taking one such integral. So can I erase this now? I'll come back only to that. So let us say I take one term here, any one term. So the first term. So half is also not important. Sum is also not important, but let me write this. Delta chi I star 1, chi j star 2, 1 by R1 2, chi I 1, chi j 2, beta 1, beta 2. So this is my term. This is the first term that I am writing. Is it okay? So, except that everything has to be taken. That's okay. It's not important. How do I write it in this form? That's what I am going to show. Remember, you have an integral over beta 1, beta 2. I first perform the integration over beta 2 because this is a function of 1. So, I integrate this quantity with beta 2. I am allowed to do that, right? If I integrate this quantity over beta 2, this will be a function of beta, not beta 1, function of 1. Beta 1 is not right. Beta 1 is a volume unit, infinitesimal volume. So, this entire thing will now become function of 1. Some function, I don't care what it is. So, I can write this as an integral delta chi I star 1 function of 1. And then you have a beta 1, which is exactly in this form. So, each of the terms I can write it in this form. After integrating over the coordinate 2, I have a situation where something will be function of 1 which multiplies with delta chi I star 1 everywhere and gives you 0, because my delta L has to be 0 finally. And then I can interpret that whatever this something in every term, I am going to collect, of course, plus plus plus, all that together is going to become 0. Is it clear? So, from every term I will have this. So, this f of 1 is going to be collected over these, over these, over these, over these, over these, over these, everything. And then I can say that entire thing is equal to 0. Okay? I can do that collection. So, let me write it down. Sum over I delta chi I star 1. And then I have some term which I just call it now x of 1, beta 1 equal to 0. That's what I am going to get. Finally, I am going to get this form. That x of 1 contains everything. This one integrated by 2, 2, 2, here, here. Here, of course, there is no integration over 2. It is simply h of 1 chi I. Here, it is a very simple thing. So, this is what I am going to get. Except that the x I am going to write in full later. Sum over I equal to 0 for each delta chi. Please note that this x is nothing to do with chi. This is x. It could be y, whatever. If you don't like x, I can write y. It doesn't matter. Just to make sure that don't get confused. Write x, y, z, whatever you want. So this is the generic form of the equation that I will have. Except that the y of 1 has to be now expanded from that list of terms on the left hand side. Is it clear? So how do I make it equal to 0? The two things I am going to do. One is a sufficiency condition. The sufficiency condition tells me that under summation over I, each term is individually equal to 0. So I am going to use a sufficiency condition, and this is usually, of course, you can argue with that is this the only condition. So I am going to say for the sufficiency condition that each delta chi I star 1 integral, of course, y of 1 beta 1 is 0 for, of course, each I, but I am not going to sum for each, not I, each delta chi, all values of delta chi. Please correct it. Because when I have a sum over I, how can it be for each I? That is nonsense. What I mean is that for all arbitrary delta. That means I can change chi I arbitrarily to delta chi I. See what I was doing, I was changing x to delta x. Remember my x square problem. Delta x can be any arbitrary change. Similarly, for each chi I, this delta chi I is arbitrary. That's what I mean. The fact that we are changing for each I, that is obvious. So that is what I meant. So but what I am now doing a sufficiency condition is that I am not putting the sum over I. I am saying under the sum, each term is 0. If under the sum, each term is 0, of course the sum is also equal to 0. So that is the reason it is called sufficiency condition, but not necessary. Because you can argue that for one I it can be negative, another I it can be positive, and it can eventually make it 0. So this is an argument that we are not doing. So we assume the sufficiency condition. Then I say that for each delta chi I and of course each I, now both, it is equal to 0, and then I use this AB equal to 0 to say that y of 1 is equal to 0. Since it is for arbitrary delta chi I, for y of 1 is equal to 0, for whatever I it will come. So we will have to only identify this y of 1, which is the 1 electron function. Interestingly, this is a 1 electron function. The equation that I am getting from a very complicated n particle variation has now been reduced to a single particle equation. I want to tell you that I have got a 1 particle equation. This y obviously has one term which is h chi I. I think the first term is quite obvious to see. It starts with h of I 1 chi I of 1, right? That you can easily see because the first term is an integral delta chi I star 1 h of 1 chi I 1. And then of course the rest are all there, which also includes chi. So this quantity, this function of 1 is of course a function of chi, the spin orbitals, but it's a single particle equation. That is important. And we will show that this is precisely the equation which is called the Hartree-Fock equation for spin orbitals. Of course, since it's a single particle equation, if I can get this equation in the form of an eigenvalue problem, it will become orbitals or spin orbitals. If I can get it as an eigenvalue problem, we will see how to do that. But essentially, this is the 1 particle Hartree-Fock equation that we talk of. And many of you already know that the Fock operator acting on something equal to something. So all that will come as a y of 1. I mean something minus something equal to 0. But this is the spirit of the Hartree-Fock variation. Yes. Yes, of course. Yeah, I'm talking about entire term.
Thus, the complex conjugate of all terms.
Okay.
So the complex conjugate can also be written in terms of.
Yeah, you can. Now, the point is, it's a sufficiency condition. So, if this is 0, conjugate is also 0. So, that is the reason I should have mentioned that in the sufficiency. It is not only that for each I it is 0, but I am also assuming for delta L to be 0 first that this is 0. So, I have another two sufficiency conditions that this is 0. This itself is 0 is the first sufficiency condition. Because if this is 0, conjugate is automatically 0. Then the second sufficiency condition is that under the summation over I, each term is 0. Under the summation over I, each term is 0. But remember now, if you look at the second term onwards, there is a summation over I for delta chi I, but there is a summation over j. Where does that j go? That j will actually go in y of 1. That is hidden now. Because I am only talking of sum over I. I wrote the entire equation as sum over I delta chi I star into a function of 1, which I told you is an integration of the whole thing over d tau 2. So that y of 1 will now actually include function of j, sum over j. Okay, so that has not vanished, the two summations. So I already said this here, right here. So I had a sum over I, sum over j. So the sum over j will be anyway performed. So your f is now sum over j, this quantity. So when I will identify the y of 1, the sum over j will come. So the point here I am trying to say that every entire equation I am trying to write as a delta chi I star I something integral 1 sum over I, only sum over I. So basically I am trying to write it in this form. This quantity will now contain the second electron, just as here, the second electron, integration, d tau 2, plus all the summation over j wherever required. Wherever required. For example, the first term, of course, there is no summation over j. It is just h1 into chi I1. Wherever required. So everything will come, including the Lagrange multiplier, this summation over j. Everything will come in y of 1. So right now, it's just a function, abstract function. Important thing to realize that because these integrations are over all d tau 2, wherever 1 and 2 coordinates are there, that integration is performed to get y of 1. Because if I perform the integration over d tau 2, I have only a function of 1. Is it clear? So y of 1 is a very complex function. It will include all the terms like h of 1 chi I1, all summation over j, all integration over d tau 2 wherever required. Okay. So I think this is something that we should remember for when I will do this y of 1. So the y of 1 is something that I will try to detail from the next class onwards. And actually you already know how I am going to do it, so it's very easy. So it's basically the first term of y of 1. For example, the y of 1, the first term is itself h of 1 chi I1. That is clear. This is very trivial because then when I integrate here, I get delta chi I star 1 h of 1 chi I1. So that's the first term. The second term will start, I can generically show sum over j, integral chi j star 2. I can write it right away. 1 by r12 chi j 2 d tau 2 multiplied by chi I1. Note that this chi I1 must remain. Right? The integration is over chi j 2, but this chi I1 you cannot vanish because I want to write everything with only one delta chi I star on the left. Everything else should remain. So this chi I1 will be a part of the y of 1, and I can keep writing like this. I have just written this chi I1 later because I am not integrating. I am first integrating over d tau 2, so I am allowed to bring this here and then write chi j1 later. So and then go on. In fact, we will do this thing in the next class. I think he has to also go. We have to go now, right? Yeah. He has another video recording, so I think we'll also stop here today. So this is how it will happen. As far as y of 1 is concerned, and all this together will become equal to 0, which will give you the single particle Hartree-Fock equation. Okay, is it clear? So 2-3 very important things is that the Lagrange multiplier L Lagrangian is Hermitian. Lagrange multiplier is also a Hermitian matrix. That's a matrix. Remember, this is a scalar. Remember, this is a scalar. This is a matrix, Hermitian matrix. Okay, and then we are using a sufficiency condition that for each summation over I, within this summation over I, the entire all the terms for each I is equal to 0. And what is the other sufficiency condition that we said just now? So for all I it is 0, and the complex conjugate also is we are not going to consider. So first is that all the terms are going to be equal to 0, and then within this term for each term is 0. So these are the two sufficiency conditions I am going to use, so that I don't have to bring in the concept of complex conjugate. So conjugate automatically, if this is 0, the conjugate will become 0. So that will be the first part to show. Then the second part is under the summation over I am going to write only summation over I. Summation over j will all be hidden in y of I. So under the summation of I, for each I, the terms which survive are also equal to 0. The two sufficiency conditions I am going to use in deriving the Hartree-Fock equation. Alright. So I will stop here.